Good morning and welcome to the beginning of the 26th International Master Course in Theoretical and Practical Application of the Finite Element Method and CAE Simulation and the international version, which is now in its 9th year. My name is Juan José Benito Muñoz. I am a professor at this university, Universidad Nacional de Educación en Estancia, UNED, and I am also the director of this master course. As I am largely responsible of this master's degree course, and to a certain extent the main host of this inaugural session to our course, I will begin the speeches by welcoming especially our students who will see us later on via our virtual classroom. I would also like to welcome our teachers, administrative staff, as well as our global and local partners. As every year, in this session, I would like to briefly explain the structure and the content of the course, and this year also some new developments. We have always been of the opinion that any professional should have totally assimilated the theoretical basis and their subject, and be ideally trained in the use of the best tools to carry out their work. This notion, which from the beginning has caused us to look for a balance between the theory and practice, is evident in the title of our course and can be observed in the structure of each module with 3 evenly balanced parts, fundamentals, application, and practice, and the course materials, which includes theoretical texts which have been especially produced for this purpose, and the best professional software on the market. Furthermore, the growing demand for specialization is clear, and this addresses in the global structure of the course with basic and specialized modules. The first, the basic modules, include theoretical and practical fundamentals. The purpose of this is to bring people's knowledge up to the same level and is therefore compulsory. This will aid further development at more advanced levels. This module has 30 CTS and it must be fully completed. This has been a drawback for some students who have not been able to do the required work due to their professional duties. For this reason, we have decided to distribute its content over several modules called MB. This can also be useful for people interested in the study of only some of the subject of the basic modules. The second type of modules are the specialized modules, and this involve in-depth analysis of different areas using theoretical and practical knowledge. I would like to speak about the beginning of the course before finishing my comments about the nature of the course, because they partially explain its structure. I remember how in 1992, Miguel Ángel Moreno, director at that time of XXVI, and I had the idea of putting together a course on the finite element method as part of our new university summer course program in Ávila. This was the initial spark to become our master's course. We first met in INITEC, an important project office at that moment, where we widely use the finite element method. Not long before, Miguel Ángel Moreno, Ronald and Carlos Arias had founded in XXVI, which had the sole rights to the ANSYS code for Spain. I had already taken the plunge with the university whilst maintaining a close relationship with INITEC. So it was thanks to these circumstances that with great enthusiasm we put together the summer course with the same theoretical and practical characteristics that I have mentioned earlier. We repeat the experience, and after further course in XXVI, we decided to organize a postgraduate course based on these ideas while making use of the distant learning methodology of our university. The first course got off the ground in 1994 and was a success. Given that a sizable section of our students were professional in work, the distance learning format was ideal. Moreover, the balance between theory and practice with a commercial code like ANSYS result novel and attractive. Since then, new modules have been incorporated. The first 3 morphed into 5 the second year, and today we currently have 15 modules and new commercial codes for carry out practical exercises. The distance learning model eliminates geographical barriers. 9 years ago, due to demand, we decided to add an English version in a clear bid to internationalize the course. Now, it only remains to say to our students that we hope this course fulfills your expectation and you find it useful. And finally, I would like to welcome you once again. Thank you very much for your attention.
Now we will present the prize for the final master project of the last edition of 2019. The prize goes to Wolfgang Artner. Congratulations! But there were many final master projects that were very well done, well performed. So congratulations to all. It was difficult to choose a winner. The tutor was Román Martín, and we will give about 45 minutes to Wolfgang to present his project.
Welcome to this presentation of my master's final project with the title Dynamic Analysis of a Machine Tool. This project was the final part of the work done in the International Masters in Theoretical and Practical Application of the Finite Element Method and CAE Simulation. Let me introduce myself. My name is Wolfgang Artner. I'm the General Manager of an engineering consultancy company called Abotec, which is located in Bad Vöslau in Austria. The last 2 years I participated on the unit FEA Master's Program, and as already said, this project that I will present you was the Master's final project. Let's start with the motivation for this project. As you can see on the left side, which this picture shows a typical machine tool. Machine tools are used during the manufacturing process of parts, especially cutting machine tools are used for processes like turning, milling, or grinding. Machining of components is one of the most important class of manufacturing processes, and therefore the machines used in this process have a high importance in industry. A modern machine tool is a very complex mechatronic system where the design of the mechanical parts as well as the electronic devices, electric power devices, or controller systems are very important to play together to create a powerful machine. From the process side, one challenge in the design of the machine tool is to avoid chatter vibration effects as best as possible. So the goal in the design of the machines is that these effects have to be studied in advance and to be minimized as goal from design. You can't avoid them absolutely, because there are some self-exciting effects on chattering, as you can see on the left-hand side, where the principle of the sources of the chattering effects is explained. So the stiffness of the machine as well as of the cutting process, together with the damping and so on, builds a spring damper system which might be self-exciting when the system parameters like cutting speed, feeding speed are in a specific range. So this depends on the process as well as on the machine. But however, one can optimize the machine side and therefore create a good design for machines. On the right-hand side, there is a picture where you can see the result of these shattering effects that leads to rougher surfaces as expected, as well as deviations of the let's say perfect or the required shape of the parts that are manufactured. So the aim of this master's final project was to perform a dynamic analysis of a machine tool to indicate design parameters responsible for chatter vibration effects and the overall machine precision that might influence the quality of the manufactured parts, surface and shape. So let's have a look at the state of the art in a machine tool design or machine tool analysis. Most often the so-called modal analysis is used. The modal analysis shows the eigenvalues and eigenvectors of a system. And this can be done by numerical analysis, like the FIA method, as well as with measurement methods, so by physical tests. Another method is the so-called frequency response, or in short term FRA analysis, where the structure is excited with unity force in unity force at the tool center point, and then the frequency of this exciting force is changed in a defined frequency range. And then the response to this exciting force is measured, and a typical graph for that is this shown Baudet plot that you can see here at the center, where the response amplitude and also the phase angle of the response is shown together. With the information from the frequency response graph and the frequency response transfer functions, the response to specific process or specific process parameters can be calculated. This needs information about the cutting tool parameters, which are included in the so-called force direction factors, as well as of the feeding direction of the manufacturing process, which is included in the motion direction factors. As long as these factors are linear and can be included in one linear factor, this linear system can be used. The disadvantage is that all nonlinear effects have to be neglected. For many cases this might be sufficient, but as you will see later on, in some situations it is not, and then other methods have to be used. For example, the so-called flexible multi-body dynamic analysis. In a flexible multi-body dynamic analysis, the simulation is always nonlinear, which means that we can simulate large motion of the components, as this is typical for manufacturing processes. We can include nonlinear stiffness and damping behavior of components, and it is possible to include formulations that allows a realistic discretization and idealization of linear guides, ball screws, or other machine components. The multi-body dynamic simulation could also be coupled with control software simulation in a so-called co-simulation. When we use a linearization of the component's elasticity, we will see what it means later on. A significant speed up can be achieved, but this means that the components itself show a linear behavior, as it is also a foundation of the FRA or modal analysis discussed before. Additionally, to the previously explained goal of the analysis is an objective that to compare the finite element based frequency response analysis, short FRA, with the multi-flexible body dynamic analysis with the shortcut MFBD. With respect to accuracy and reliability of the results. And beside this, it was also one goal to identify any problems in the current design of the used machine tool and to propose possible improvements. So which tasks were included in the project? At first, I want to mention that the software packages FINITE with NX was used for the finite element related analysis steps, and the software Ricodyne was used for the multi-body dynamics simulation. So in the first step, the modal analysis has to be done with the target to identify critical modes and corresponding frequencies. In the next step, the frequency response analysis was done with the goal to identify critical operation conditions. Step number 3 was the so-called dynamic reduction of the components. This is also called super element technique because this dynamic reduced components are used later on in the nonlinear transient dynamic NFBD simulations. Okay, let's have a look at the machine that was used in the simulations. It is a game tree type 5-axis milling machine was used. As you can see, it is quite a large machine with an x-axis stroke up to 4,400 millimeter, a y-axis stroke of plus minus 850, and the z-axis stroke of about 1 meter in total. The machine design was based on a present machine at one of our customers, and we took the other dimensions and designed a similar machine, let's say, as reference for this project. The overall mass that you can imagine, the size of this machine is about 14 tons, so it's quite a large structure. And the excitation frequency range of interest was estimated to be up to about 225 Hertz. In the model, the milling head, so the last two axes, the two rotational axes, were not included, so the model itself includes just the 3 translational axes, and the simulations are focused on this simplification of the real machine. So at the beginning of the project, because it was already clear that a lot of different simulations have to be done, a proper modeling strategy has to be defined. And it was, the decision was that it is not used, that it might be common in other projects, to do everything out of the FEA preprocessor by interactive working with the graphical user interface. And to start the solver out of that, it was decided to use a strategy that is based on the input file and the Nastran input file that is sent to the solver. This input file can be prepared manually, and you see on the left-hand side in this graph the structure of the Nastran input file. So in the yellow box at the top you see the general solution settings block, and in the red frame you see that there is the so-called bulk data section where the FEA components are included, the material is included, and also coordinate systems and so on. And this is used with the fact that all grids referenced in this bulk data sections use a local so-called reference coordinate system number. And by modifying this local coordinate system, for example, you change the x, absolute x position of this reference coordinate system, you can move your related components. And this strategy is very, very powerful when you set up a structure, a machine with alternative positions of single components. And additionally, if you want to substitute one component with a newer revision of that component and so on, you only have to change each component file, which is the file where all the nodes and elements are included that are referenced by one component. And the only thing that has to be changed in the master file is the path to that file that is referenced with the include keyword. So this is a very, very powerful method. And as you can see here on the next slide with several pictures, it is easy to switch between the different positions, in that case of the vertical axis, just by modifying 3 parameters of a coordinate system. That's all. Okay, so this was the first development step in the project. And the next thing that has to be done, of course, is to create the FEA model itself. I focused on mesh quality because it is clear from the theoretical side that the better the mesh quality is, the more reliable are the results that are retrieved from the simulation model. And in this case, we used mostly 4-node plate elements with additional some beam elements or some solids elements. And the best shape for this 4-noded plate elements are a pure quadrilateral shape. And yes, as you can see on these pictures, this is tried to get best mesh quality as possible. Another thing to mention is when we work with these alternative positions, how to establish the connection between, for example, here the portal of the machine and the mainframe. As you can see on the left, you see the cross slider and the 5 rectangular plates there. And these plates represent the shoes of the linear guides, and they are connected to the mainframe via so-called glue contact definitions, and this allows an connection of the mesh even the nodes are not coincident, and this is a very powerful functionality of an ASTRAN to use this glue definition. Based on this finite element model, the first step was to perform the modal analysis. And here you can see the results of one specific position. So there were several positions studied, but here are the first critical modes. And you can see the first mode start about an eigenfrequency of 23 Hertz, which is quite low. And the eigenvectors are mainly related to the motion of the milling head together with the vertical axis, and the weakest part of the structure are the linear guides of the cross slider table, which is the connection between the vertical axis and the horizontal y-axis, which is the transverse axis. Okay, the eigenvectors which are shown here in the color plot are related to the z-axis, to the portal itself, and so on. But it also can be seen that up from 200 Hertz, the eigenmodes are related to plates that are located somewhere in the mainframe, the stiffener panels, and are not related to large masses on the structure. They are just in the mainframe, and these effects have to be taken into account when comparing modes, or also at the FRA analysis. The frequency response analysis, the typical result out of that is the so-called Bode plot, where we can see here are two Bode plots shown. At the top of the plot is the response amplitude shown. The horizontal axis is the frequency range, and on the top and the bottom of the graph there is the according phase angle relative to the excitation. The frequency response analysis is excited via a unity force. In this case it was 1 kilonewton, and this is a fundamental of this method. This force varies harmonic, so the response is also harmonic as well. As we can see in the graph here is that on the right hand side this is the response to the excitation in the y direction, so a transverse excitation, and here the response amplitude is more than twice as high as on the left hand side. You have to take into account that the vertical axis on the top is a logarithmic one. So here is the according table shown that have a look at the column position 1 with the y excitation, and there we see that, for example, we have a response amplitude of 2.4 millimeters, while the response to the x excitation is just 0.88. So it's more than double related to the x excitation direction. So this indicates that the weakest direction is the y direction. Okay, we prepared the model for the subsequent analysis in the multi-flexible body dynamics analysis, and as I mentioned before, to include the flexibility of the structure, the so-called modal reduction or dynamic reduction has to be done. And what is behind that reduction? That we want to reduce the amount of degrees of freedom to which allows a speed up in the analysis, but with less loss of accuracy as possible. In mathematical sense, which is the formula is written here on the right hand side, means that we have a transformation matrix, which is here called TC, and the remaining degrees of freedom in a vector called UC. And the transformation matrix consists of two different parts. The submatrix B is the so-called static condensation matrix, which is just the stiffness related reduction from a full set of degrees of freedom to some master degrees of freedom. And in the submatrix Phi, there are some additional internal, so-called internal modes included, and these modes are then related to the coordinates called QM. And let's see how this process works. It's just a mathematical definition. In the FEA program, in this situation we used an ASTRAN, as mentioned before. We have here the degrees of freedom from the full system, from the FEA model, and there is the so-called static condensation done at one hand side. These modes, modes are called constraint modes, even that are not really modes. They're just the deformation shapes based on a unity displacement on the single interface nodes. And with the interface node fixed, then there is a modal analysis done. And these modes that are calculated then are called fixed boundary modes. And altogether, these are the degrees of freedom of the reduced structure. So there's one problem still left, which means that the constraint modes and the fixed boundary modes are not orthogonal to each other, and therefore an autonormalization has to be done, which requires a second modal solution. And at the end, there are just some modes left that describe the dynamic behavior of the reduced structure. So this is a really powerful method, but one has to take care that there are enough fixed boundary modes included to represent the dynamic behavior in an accurate way. How can we do this? Or how can we check whether the generated reduced bodies are accurate enough? For this purpose, we can use the so-called modal assurance criterion, or short MAC. This is well known and established for a long time in the field of measurement, of modal analysis by measurements, and used for the comparison of different mode shapes and eigenvectors. The typical result of this MAC criterion is a so-called MAC plot, where each column and each row represents one mode shape of a set of mode shapes of one reference design or reference measurement or reference simulations to another one. And in this graph here, it means that here on the main diagonal, this red squares, these red fields mean there is a perfect correlation. But here, between the two different models or measurements, and here in this region here, there is not a good correlation. So the eigenvectors do not relate really to each other. So in our specific model. Here is one a comparison between the reduced structure and the non-reduced structure modal results. And as we can see here is that we have really a good correlation on the main diagonal up to here the mode number 15, 16, and then there is, let's say, an not so good correlation. But what's the reason for that? As you remember, on the pictures shown before from the modal analysis, there were the higher modes up from 200 Hertz approximately. There are the vibration effects of the stiffener panels of the mainframe, and they're all in a similar frequency range, but of course the eigenvectors are different, and therefore you see such a big deviation here in that region. So overall it can be seen that the selection of the component modes during the CMS reduction is a key factor for the accuracy of the subsequent multi-body dynamic analysis, and several trial and error loops were required to retrieve high quality results, since it is not possible to define the required modes a priori. Okay, so in the flexible multi-body dynamic analysis, as discussed before, a requirement for the frequency response analysis in the FEA-based frequency response analysis, this analysis requires an averaging of the force and motion direction factors. And this means that in average over the process, the direction of the acting force can be treated as constant. This is true, or let's say not true. It's the failure that you do is small enough when the number of blades, for example, on the milling tool is large enough and under specific milling conditions. But if you use, for example, end mills that normally own 2 or 3 blades, then their direction factors are definitely time dependent, and which results in varying forces and also non-harmonic excitation forces, which was also an requirement of the FRR analysis. In addition to the number of the blades, the milling arc, which is the angle from the tool where the cutting process acts, is not 180 degree, then we will also see some special excitation effects. The nonlinear transient multi-flexible body dynamic analysis will allow to include these effects in the simulation. This is more realistic, but the drawback, of course, is it results in longer simulation times, and you always focus on a specific process. Here you can see on the left-hand side the multi-body model created, and on the first look you see there's not really a difference to the graphical representation of a FEA model. Why? Because all the components here are linearized FEA models, these model reduced bodies. But the MFBD model also has elements that helps to represent specific machine components as linear guides or ball screws, which are very important for the correct setup of such kind of machine tool model. For the performed studies, as explained before, cutting force model with 3 blades instead of multiple blades was used to show the effect of this non-harmonic excitation. To explain that, you see here on the right-hand side the a symbolic representation of the milling tool. So the large circle is the outer diameter of the milling tool, and the three small circles are should represent the cutting blades. And so this is the outer diameter of the milling tool, and these are or let's say the center of the smaller circles. There is the cutting blade located. Here we see a situation. The milling arc is 180 degrees, and the blade number 1 is acting and cutting. And since we are here located at the angle 0 or 360 degrees, the cutting force is horizontal, transverse to the feeding direction, which is our vertical axis. When we rotate now, in this case, the 30 degrees, then the next blade comes into contact with the material, and we see a change in the overall force, cutting force vector. This can be continued, so we rotate 30 degrees far more. Both cutting blades are in action, and we see that the force direction is rotating back a little bit in the horizontal position. And at the end of the cutting arc, remember the cutting arc is 180 degrees. The blade number 1 leaves the cutting situation, so there is no cutting force acting anymore, and the only force that is acting acts on this second blade, and therefore the vector is pointing downwards. So as you can see, the resulting force vector is moving around in an angle window that is let's say about plus minus 30 degrees approximately. So, and this is an important thing for the simulation. Here are 4 different scenarios shown that represent the different milling arc positions. The described before is the one on the left top left hand side. So we start here at 270 degrees and leave at 90 degrees relative to the feeding direction. And one can see that each blade has a kind of smooth half sinusoidal function here. But when one reduces the angles, then it can be seen a relative or moves also the milling arc relative to the feeding direction, that the acting force is absolutely non-harmonic anymore. And from these functions you can estimate that different dynamic effects will result out of this. So this this could be shown with the multi-body dynamic analysis, and from my point of view, the most meaningful graphs are shown here, which are called orbit plot, which means that even the tool center point moves the used motion path was just a straight line with the defined milling arc definition. And the graph shown here is the deviation from the tool center point from its ideal position. And here we can see that the kind of deviation that results through the dynamic behavior of the machine is absolutely different depending on the characteristic of the acting cutting force here. So this is was the main result that could be retrieved from the flexible multi-body dynamic analysis that could not be shown with a frequency response analysis. So based on this performed analysis, a modified machine tool design was developed. So more in detail, 2 different design attempts were done. The first one was just an increase in the machine stiffness with in combination with a best as possible mass reduction on the machine. So this was strategy 1. The second strategy was to use a tuned vibration absorber system mounted at the vertical axis end and try to reduce the vibration response with such a kind of system. It could be shown that the stiffness improvement reduces the response amplitudes as expected, and that with let's say more effort, it could be reached that all the eigenfrequencies or let's say the significant eigenfrequencies can be shifted out of the excitation range of interest. But it is not possible to eliminate all eigenfrequencies out in a range of excitation, because this machine would be so stiff that it can't be built. The other attempt with the vibration absorber system seems also to be a very has a high potential, but the tuning of the parameters is, let's say, needs also more studies on that topic. And yes, both designs would require more detailed analysis to reach a qualitative realization level. At the end, it was shown that both analysis methods, the FE-based frequency response, including the modal analysis, as well as the multi-flexible body dynamic analysis, have been proven as a powerful tool in the design and analysis of machine tools. Even a lot of simplification and assumptions are related to the frequency response analysis. This method is preferable in the early design process, since the obtained results were found as conservative, and the higher solution speed plays a key role in performing fast but reliable results of different designs. The multi-flexible body analysis is advantageous over the FRA when it's getting more complex, which means nonlinearities and time-dependent effects have to be taken into account. So especially when one is interested in a specific situation as benchmark for the machine qualification or something like that. The analysis workflow, including the developed modular setup, is well suited for usage parallel to this design process and delivers fast results of high quality. Overall, the combination of both simulation methods seems to be the best strategy for analysis tasks related to the mechanical design of machine tools. Thank you for your attention, and goodbye.
Thank you very much, Wolfgang. It was an incredible and awesome presentation. Just to finish and end this inaugural session, we just stay tuned to your modules, because each of your tutors or professors will present their own module for the FEM general theory, numerical calculation, programming, material laws, and of course for the practical and application subjects for ANSYS, pattern, and civil FEM. Okay, Thank you very much, and see you in the platform classrooms. Bye. Thank you.